Hello, this is Richard Hammack's Calculus 1 course, and we're in part 4 of the course on applications of differentiation. Our previous lecture, 34a, introduced optimization problems, where the goal was to apply max and min techniques to practical problems. Today we're just going to continue that by working a few more examples. So let's jump right in. First example. Find the point P on the graph of y equals x squared that is closest to the point 18, 0. So here's the picture. You've got the graph of y equals x squared, a parabola, and way over here on the x-axis, 18 units down, is the point 18, 0. So we're looking for the point P on the parabola that's closest to that point 18, 0. Let's take a typical P, like this one, on the parabola. It's some distance away from the point 18, 0. And we could move along that parabola and get a little closer to the point 18, 0, like right here. And it looks like if we come out like this, we're even closer. But now it looks like we're getting maybe further away from the point 18, 0. And clearly, the further up the parabola you go, the further away you're going to get. You may have a feeling that the point P on the parabola that's closest to the point 18, 0 might be somewhere around here. So this problem is to find that point P exactly. To find this point P means to give its x and y coordinates. So why don't we call its x coordinate x? And then what's its y coordinate? Well, it's on the graph of y equals x squared, so the y coordinate would be x squared. So P has to have the form of x comma x squared. So for any x, there's a point x squared on the parabola, and we're looking for the point of that form that's closest to the point 18, 0, that minimizes this distance. So right there you can see that this is a minimization problem. We want to minimize distance. Now to find the minimum distance, we would need a function that gives us the distance so that we can find its absolute minimum. So let's think about how we would do that. We want a function of x that tells us the distance from P to 18 on the x-axis. Well, one thing that you'll see here is that there is a right triangle where the distance is the hypotenuse. So perhaps we could use the Pythagorean theorem. We'd need to know the lengths of the legs of that triangle. The vertical leg is easy to find because that's the y coordinate of P, so it's going to be x squared. What about the horizontal leg? Well, we're way over at 18 at one corner, and at the other corner we're at x, so the distance between those two corners would be 18 minus x. So good. Now we can use the Pythagorean theorem to find the length of the hypotenuse, which is the distance from P to 18, 0. And doing that, we would get that this distance is the square root of 18 minus x squared plus x squared just by the Pythagorean theorem. And foiling out the 18 minus x squared, that's x squared minus 36x plus 234, plus the x squared squared is plus an x to the fourth. So we see here that we need to find an x that minimizes this distance, d, that we have up here. Now we're looking for an x that minimizes distance, and this distance has a square root in it, which is fine. But here's a trick that you might want to think about. It's easier if you didn't have a square root, but if we're looking for the x that minimizes distance, d, that's going to be the same x that minimizes the square of distance, d squared. It's easier to do that. So it's easier to find the x that minimizes d squared, which is x squared minus 36x plus 234 plus x to the fourth. It's easier to work with this expression because that's a polynomial, and polynomials are nice. So phrasing this in terms of functions, we want to find an x that minimizes this function of x. Let's write that down very carefully. We want to find the x that gives the absolute minimum of the function f of x equals x squared minus 36x plus 234 plus x squared on an interval. And what would the interval be? Well, remember, x could be anywhere on the x-axis that it wants to be. So the interval is from negative infinity to infinity. So now that we've analyzed this problem, everything from here on out should be pretty mechanical. We just want to find the absolute minimum of this function on this infinite interval. And we know we have to find the derivative of f to do that. We want to take its derivative, set the derivative equal to 0, and look for critical points. So start by taking f prime of x. It's 2x minus 36 plus 4x cubed. And we're going to set that equal to 0 so we can find the critical points. Now let me put the highest power of x first, and so the x cubed is right there, and notice that every coefficient here is a multiple of 2, so we can multiply both sides of this equation by 1/2 just to make the numbers a little more manageable. And doing that gives us the equation 2 cubed plus x minus 18 equals 0. So to find the critical points, we need to solve this equation. Now notice this is not a quadratic, it's x cubed, so we can't use the quadratic formula, and maybe factoring will work, but it's going to be an intricate sort of factoring. If you play around with this for a while, just trying to factor it, you'll eventually hit on the fact that it factors as x minus 2 times 2x squared plus 4x plus 9. So we get this product equals 0. And right there you can see you're picking up a critical point of 2 from this factor, and maybe this other factor will factor further, will be equal to 0, and would give you another critical point, so you need to examine that. You'd have a hard time factoring 2x squared plus 4x plus 9, so then you might turn to the quadratic formula, and here's something that you would soon realize, that this polynomial 2x squared plus 4x plus 9 has a discriminant b squared minus 4ac, which is part of the quadratic formula. That's 4 squared minus 4 times 2 times 6, and that's less than 0. And remember, this discriminant, the b squared minus 4ac, it's what's in the square root in the quadratic formula, and it's negative. And that means that this polynomial simply doesn't have any real roots. The quadratic formula doesn't return anything. So this expression is never equal to 0. So you're not going to pick up any critical points from that factor. So you can see here that the only critical point you get is x minus 2. The second factor has no solutions. So just one critical point here. So that's good. Critical point of 2 on the x-axis. We next need to look at the sign of f prime of x. Now, to do this, notice that if x is greater than 0, the x minus 2 is positive, and if you plug in a positive number bigger than 2 to 2x squared plus 4x plus 9, everything in sight is positive, so that's positive. Now, if x were less than 2, the x minus 2 is negative, but notice that there's some values of x that give you a positive value for this polynomial. We just plug one in after all, and there are no roots, so this can't cross the x-axis. It can't ever become negative. The 2x squared plus 4x plus 9 is always positive. So if x is less than 2, this f prime is a negative times a positive, and that's a negative. So our function f was, which is, remember, is the square of distance. It was decreasing until x got to 2, and then it started increasing. So you have an absolute minimum of f of x at x equals 2. And that's the value that minimizes distance squared and consequently minimizes the distance d. So the answer, the point that's closest to 18, 0, it's the point on the parabola with x coordinate 2, so its y coordinate is 4, 2 squared. So the answer is the point P equals 2, 4 is closest to the point 18, 0. So you might think that maybe this is not a practical problem, and you're right, it's not. However, the kinds of thinking that you had to use to get the answer to this problem is really valuable. And that's why you'll see a lot of problems of this type mixed in with the more practical ones. Let's move on to our next example. In this example, let's say you have a rectangular piece of sheet metal that's 18 inches wide, and you're going to construct a gutter from this piece of sheet metal by bending it in the following way. First of all, you're going to divide it into 3 equal strips that are each 6 inches wide, and you're going to bend along the dotted lines, as indicated here. And you're going to form a gutter. This left-hand strip here, it turns up to a right angle that's that gives you a side of the gutter that's 6 inches tall. This middle strip is your base, and it's going to be 6 inches wide. And then you're going to have an angle here, some theta, that you're going to decide upon, giving you an angular length here of 6 inches. So you're going to make a gutter by this recipe. And the question here is, what angle theta is going to hold the most water? What angle theta would give you a gutter that has the greatest volume? So here's theta. It could be anywhere from, say, 0 to 90 degrees. So to analyze this, it's really helpful to look at the cross sections for various values of theta. Looking at the gutter from this side, and imagine it's filled up with water. If theta was pi over 2 or 90 degrees, the gutter would look like a square shape. 6 inches, another 6 inches, and then another 6 inches. And that would hold a certain amount of water. And clearly, you wouldn't want theta to get bigger than pi over 2, because that would obviously be less water. If it was angling in like that, it would pinch the water. But you could make theta smaller, like this, and that would give you kind of an overhang on the right, an angle, and it looks like you might be picking up some extra volume for the water in so doing. But you have to be careful, because you can see here if theta started to get really small, like maybe here it's 15 degrees or 1 degree, this gutter's not going to hold hardly any water at all. So the question we're trying to answer here is, what angle theta, 90 degrees or somewhat less than 90 degrees, would give you the greatest possible volume of this gutter? So from looking at these cross sections, you can see that a refinement to this question would be, what angle theta yields the greatest cross-section area? Clearly, if the cross-section area like this is maximized for a particular theta, then the volume of the gutter will be maximized as well. So let's work with this simpler problem. Let's find what angle theta yields the greatest cross-section area. And right there, you can see that this is a maximization problems, you want a function of theta that gives you cross-sectional area, and you want to find the theta that maximizes that function. And here we would have an interval that applies. Theta could be as low as 0, which would give you 0 area, and it could be as high as pi over 2. So we want to maximize cross-sectional area, which is a function of theta, with theta on the interval from 0 to pi over 2. So with that in mind, we need to find the cross-sectional area of the water in this gutter. Now this gutter is 6 inches tall on the left. Maybe that's where it attaches to a wall. It's 6 inches wide, and then you have an angular section of 6 inches that comes out like this. And we want to find this area A. And that area, it's looks like a trapezoid. Let's see if we can find it. I'm going to drop the height down like this. And we can find the height of this area of water. If you look at this triangle that's right here, the hypotenuse is 6, the angle is theta. By trigonometry, the height would be 6 sine theta, the height being the opposite side from this angle theta, where the hypotenuse is 6. By trigonometry, this height would be 6 sine of theta. And let's see, what else could we do to give dimensions to this picture? We could also find this distance right here. That would be 6 cosine theta from trigonometry. So we're starting to add dimensions to this figure. Let's think about what the area of this water would be. Notice we have a rectangle right here and a triangle right there, and together they make up that blue cross-section of water. The area of this blue region would be the area of that rectangle plus the area of the triangle. And these are familiar area formulas. For the area of the rectangle, it's going to be base times height. Now its base is 6. Its height is this, which notice is 6 sine of theta. So base times height for the area of this rectangle would be 6 times 6 sine theta. Notice it's not 6 times 6. This height of 6 here is taller than the water. So 6 times 6 sine theta is the area of the rectangle. And then we need the area of the triangle. Let's see, the area of a triangle is 1/2 base times height. So 1/2, and then the base is 6 cosine theta, and its height is 6 sine of theta. We're talking about this triangle that's right there. So its area is 1/2 6 cosine theta, 6 sine theta. Simplifying this gives us 36 sine theta plus 18 cosine theta times sine theta. So that's the cross-sectional area, and we're going to want to find theta that maximizes that. But first of all, let's think about if there's something we could do to make this a little bit simpler. Notice that 18 divides both the 18 here and the 36. So to make our work just a little bit easier, we could divide both sides of this by 18, just to knock it down slightly. And in so doing, you get 2 times sine theta plus cosine theta plus times sine theta. Let's call that our area function. A of theta is this expression, which is Well, it's 1/18th of the area A of this water. So what we want to do here is find a value of theta that maximizes this function, where theta is on that interval between 0 and pi over 2. So we want to maximize this on the closed interval from 0 to pi over 2. Now that's something we can definitely do. We've done the creative part of this problem now, and for the rest of the problem, we'll just be turning the crank because we know how to find the maximum of a function on a closed interval. The first thing we have to do is find that derivative, a prime of x. And that's easy because this goes way back to part 3 of the course. Just find the derivative of this sum of trigonometric functions. The derivative of 2 sine of theta is 2 cosine of theta. And for the derivative of cosine theta times sine theta, we've got to use the product rule. So first take the derivative of cosine theta, that's negative sine theta, times the sine theta, plus the cosine theta times the derivative of sine theta, which is cosine theta. So there's our a prime of theta. Simplifying a little bit, we get a prime of theta is 2 cosine theta minus sine squared theta plus cosine squared theta. And okay, we got to think about finding the critical point here. There's sines and cosines and squares. There's a lot going on. Let's see if we can simplify this a little bit. One thing you might notice here is that mostly we've got cosines, but here's a sine squared right there. It might simplify a little bit if we could get that in terms of a cosine or cosine squared. Remember that sine squared theta plus cosine squared theta equals 1. So this sine squared theta here is 1 minus cosine squared theta by that trig identity. And let's write it that way. Let's replace the sine squared theta with what it's equal to, which is 1 minus cosine squared theta. And now we've got some like terms. We've got a cosine squared theta here and another one there, and we can combine those. Doing that, we get negative cosine squared theta plus another cosine squared theta. That's 2 cosine squared theta plus 2 cosine theta from here, and then the minus 1 comes down right there. So that looks a little bit better. Our derivative is a prime of theta equals 2 cosine squared theta plus 2 cosine theta minus 1. So we're looking for critical points here. So we're going to set that equal to 0 and try to solve it. We want to find the value of theta that makes this expression equal to 0. In other words, we need to solve this trigonometric equation. And remember, way back in part 1 of the course when we talked about solving trigonometric equations, this is why we talked about them, because we occasionally need to solve trigonometric equations when we're doing problems like this. And we do now. We need to find the value of theta that makes this equal to 0. Okay, if you look at this, there's a lot going on, but notice that you have 2 times the cosine theta squared plus 2 times cosine theta minus 1 equals 0. That has the form of a quadratic. 2 times something squared plus 2 times that something minus 1 equals 0. That's a quadratic, and we know how to solve quadratics. To make this a little bit simpler, let's write cosine theta as x. So for the rest of this problem, we're just going to simplify it by wherever we see a cosine theta, we'll write that as an x, but we're going to remember that x stands for cosine theta. So in doing that, this boils down to 2x squared plus 2x minus 1 equals 0. And now you can see why I wanted to call cosine theta x, because you can really clearly see that we're dealing with a quadratic here. We want to find the value of x that makes this equal to 0, keeping in mind that x is equal to cosine theta, and we'll ultimately get back to theta. So we need to solve this quadratic. And it doesn't factor. You can quickly convince yourself of that. So you might want to use the quadratic formula. And if you do that, solving this quadratic with the quadratic formula, x is minus 2 plus or minus the square root of 2 squared minus 4 times 2 times minus 1 over 2 times 2. And that's 2 plus or minus the square root of 12 over 4. Now, in this problem, x is equal to cosine theta, and theta is between 0 and pi over 2, so cosine theta is going to be positive, so x is going to be positive. The negative square root here would give you a negative, so we're going to have to use the positive square root to keep x positive. And doing so, using the positive rather than the negative here, and factoring out a 4 from the square root of 12, so it's 4 times the square root of 3, and canceling on the bottom, this simplifies to x equals negative 1 plus square root of 3 over 2. Okay, so we've just figured out that in this equation, the solution that we get is x equals negative 1 plus the square root of 3 over 2. Now remember what that means. It means that cosine theta equals x. In other words, cosine theta equals negative 1 plus square root of 3 over 2. And we need to find the value of theta that makes that true. Just take cosine inverse of both sides of this equation. To isolate the theta, we get from here, theta equals cosine inverse of x, where x is minus 1 plus square root of 3 over 2. So our critical point, our only critical point, is theta equals cosine inverse of this expression. So all of this work just to find our critical point. So now let's plot that critical point on the number line. Remember, our interval was from 0 to pi over 2. We're looking to maximize this function a of theta on the interval from theta equals 0 to pi over 2. And our critical point would be somewhere in that interval. So our critical point is cosine inverse of the expression minus 1 plus square root of 3 over 2, somewhere in this interval. So we want to look at the sign of our function a prime of x on either side of that critical point. Now remember, a prime of theta on either side of that critical point. Remember from the previous slide, a prime of theta was 2 cosine squared theta plus 2 cosine theta minus 1. Let's analyze what's going on there. We could pick test points on either side of this interval to figure out whether we get positive or negative. On this side, an obvious test point would be 0. A prime of 0 would be 2 cosine squared 0 plus 2 cosine 0 minus 1. And cosine of 0 is 1, so this is 2 times 1 plus 2 times 1 minus 1. And that's positive. So on the left side of our critical point, a prime of theta is positive. On the right side, let's see, take a critical point, or not a critical point, a test point of pi over 2. Plug that into a prime. A prime of pi over 2 would be, well, putting that in over here, cosine of pi over 2 is 0. So we get 0 plus 0 minus 1. And that's negative. So our derivative a prime will be negative on this side. So you can see from this that our cross-sectional area function, A of theta, was increasing, and right here at this critical point, it started to decrease. So this critical point gives an absolute maximum. So the answer is the greatest volume for the gutter occurs when theta equals cosine inverse of -1 plus square root of 3 over 2. Now if you take out your calculator and work that out, and you might even want to put it in degree modes because it's easier to think about angles when you're building something as in terms of degrees. You're going to get very close to 68.53 degrees. So the answer, which really conforms to our intuition here, tells us that you should make the gutter this way with an angle of 68.53 degrees, which is, it's not 90 degrees, it's less than 90 degrees, so it really makes sense that there's a little bit extra room here for a little more water, even though the water level went down a little bit. That's counterbalanced by the extra area that you're adding by this little triangle. This value of theta is the one you want to use to create this gutter. So that's it for today. I hope this has been helpful. Of course, you should get lots of practice with these problems. I know sometimes you really have to struggle with them and think about them, but that's good. It's exercise for your brain. Have a great day, and I'll see you next time. And goodbye.